Alright, hello guys. I was thinking of going through the calculations from this specific document that is going to be very reminiscent of what is going to actually come up in the colloquium. And it is a mix of both AR, AD, as well as an X-linked recessive pathologies. It's for colloquium 1. You can see it right here. And it's also named Risk Calculation Medical Genetics for Colloquium 1, 2017. So this is a good document if you want to practice for Colloquium 1 since it has all three of the pathologies, and therefore you will be able to get more of a grasp of what is waiting for you. Right, let's start with the first one. Autosomal dominant pathology with 80% penetrance. So let's immediately write down the penetrance in fractions. That would be 3. Ooh, it's too thin, I think. 3 out of 5 is 80%. And they're asking for the probability that 3-1 will be affected. So this person affected means sick, right? So now we have to go according to this person's parents, which are these two people. So this person comes from population. And what do we know about population individuals for autosomal dominant? Let's go into our rule book right here. If a person is from population, assume non-carrier. Don't take into account during calculations. So that's for autosomal dominant only. So this person is completely irrelevant in our case. However, this person, this father right here, has a mother who is affected. So if we draw a Punnett square for this dominant disease right here, say looks like something like this. Then he has a 2 out of 4 or a 1 in 2 chance of receiving this dominant allele that his mother has. So this guy here, 1 in 2. However, there's still a chance, we still have to calculate the chance that he actually got the dominant allele, as well as him being actually healthy. So what is the chance for that? We have to take into account the penetrance, and therefore, if we look into our rule book again, let's see here, Bayesian table only applied for healthy individuals with a risk of carrying dominant allele. So what does a risk of carrying dominant allele mean? It means that you're not 100% sure they are actually carrying. So it's either 1/6, 1/2, whatever it is. As long as it's under 100, then you have to do a Bayesian table. So let's do a Bayesian table for this guy, carrier, non-carrier. Here we go. There we are. So his posterior probability is always going to be half of what his parents has, which is 1/2 here. And then non-carrier probability is going to be 1 minus 1/2, which is equal to 1/2. Conditional probability is always the risk for him to have this allele, this unhealthy allele, right? And also being healthy. So if 80% of the people who are carrying this allele are unhealthy, that means that 20% of the people are healthy. And we can write that as 2. Oh, I see where I made a mistake here. See? There we go. That's 4. So 20% would be 1 in 5. So here we would write a 1 in 5 for the conditional probability. For the conditional probability for non-carriers is always 1. Why? Because if you're not carrying an unhealthy allele, then your chance of being healthy will be 100%. Joint probability is this times this. So you just take 2 times 5, which in this case would be 1 over 10. And the joint probability here would be 1 out of 2, but because we want the denominators to be the same here, we just write it as 5 over 10. Now for the posterior probability, we take the numerator for the left side at the top, and then for the bottom side here, we take the numerator for the left side plus the numerator for the right side, which would be equal to, let me do this, 1 in 6. So this guy right here has an updated probability of 1 in 6, not 1 in 2 anymore. Why? Because the chance of him being healthy and carrying this unhealthy allele is much lower than 1/2 because of the penetrance being 80%. So that's his value right there. And now we have to calculate the value for the child to be sick. So we take the parent's value, 1/6, times, and let's look at our rule book again. If I remember where I put it. I don't think I put it anywhere. But it's the parent value, so you only take into account one parent in this case, times the chance for the child to be receiving an allele, and we know that it is 1/2 from the Punnett square, because if one parent is a carrier right here, right, and this parent is not a carrier, then there's a 1 out of 2 chances for this person to be receiving an unhealthy allele. So that's why we write 1 out of 2. And then times what? Times, because we want to know if this person will be affected, then he has to be part of the 80% of the penetrance. So it has to be 4 in 5. And this is equal to approximately, I think it's 1 in 15. You can also do the math and you will receive something along the lines of, I think 40 over 60. And then if you divide it by 4, you would get 1 out of 15. There we go. That's the first question. The second question is about autosomal recessive. So we have an autosomal recessive pathology. What is the probability that 4-1 will be affected? This person right here. So first off, for autosomal recessive, we need both parents in the picture. So let's see here. Yeah, I haven't written down a rule for it, but for autosomal recessive, both parents have to be a carrier if they're healthy, right? So let's say this parent is carrier and this parent is a carrier. They both have to give one unhealthy allele each for this child to be sick, because for autosomal recessive, you need to have 2 sick alleles. It's not just enough, like we did with the dominant, to have one sick allele. You have to have both of them. And if we write a Punnett square for autosomal recessive, right? Let's say it's something like this. There we go. Then you can see that the probability for a person with the parent phenotype of this combination to be sick is 1 out of 4 in total. Okay, but what is the chance for these parents to be heterozygous? Or yeah, I did use the right term this time. So we go according to the nearest affected person, which would be this person in that case. What do we know about this person? Well, if we look at the AR rule book, here we go. If parents are healthy and there is an affected sibling, the chance for the healthy sibling to be a heterozygous carrier is 2 out of 3. So if both parents are healthy and there's an affected sibling, the healthy sibling's chance to be a carrier would be 2 out of 3. And why is this exactly? So here we have healthy parents and we have an affected sibling. So this sibling that's healthy is going to be 2 out of 3. Why? Let's draw a Punnett square for this. Or actually, we already did. So we can immediately assume that this person is healthy, right? So if we look at the Punnett square here, we know for absolute certain that this person right here cannot be affected because he's not colored in, right? So there's only 3 options left out of the 4 now. And what are the amounts of heterozygous we see here? It's 1, 2. So it's 2 out of 3 because now we're counting only this one, and this one. Because this it can't be homozygous carrier because it's healthy. So that's why it's 2 out of 3. And the parents are, of course, heterozygous 100%. Why? Because they're healthy, so they have to have this dominant healthy allele. And then they're also a carrier because their daughter is affected, and the daughter has to have gotten one from the dad and one from the mom. Next up, we go according to the half rule. Why? Well, let's see here. Where there is no other way to find out heterozygous probability, you take the heterozygous probability of a first degree relative and divide it by 2 or divide it by half. So if this one's 2/3, first degree relative would be this one, and that would be 1/3 instead, because half of 2/3 is 1/3. So we see here we have 2/3. So all of the first degree relatives would be 1/3. Now, who are the first degree relatives for this person? Of course, we already know that his parents must be 100 and his sister is, of course, affected, so we don't count them in, even though they are first degree relatives. But first degree relatives are what? First degree siblings, children, or parents. And again, we already know that this sibling is 100% affected. The parents are 100% a carrier. So now we can only go according to the children, which would be only this child, but also this child. And I'll get to that in a second. So this girl right here will have 1/3. Why? Because half of 2/3 is 1/3. So what about this person right here? Why did I talk about him? Well, we can see here that this person has been married 2 times. Once to this person and once to this person. And they both gotten children respectively, hopefully. But yes, they've gotten children respectively. So the chance for this person right here to be a heterozygous carrier would also be half of his parent, because this is his dad right here. So that's 1/3. Now getting to these persons, these 2 individuals right here, they would also be 1/2 of their parents. So that would be 1/2 of 1/3 is 1 out of 6. Now we can calculate the final probability for this child to be affected. So we take mother's chance to be heterozygous carrier times father's chance to be heterozygous carrier, and then we take times the chance for this child to be affected, not just a carrier, but both small alleles, right? And we go according to the Punnett square. We can see it's 1 out of 4 in total. So that's where you write 1 in 4. And this will equal to 1 out of 144. Next up is X recessive lethal pathology. And if you know anything about XR, when we have something lethal, we have a thing called Haldane's law. And it's an exception if the illness is lethal and there's only one male affected, only one. So if we go back here, we do know that is lethal, but we have two males affected. That's why this will not be Haldane's law. We're not dealing with it right now. Instead, it's a normal XR pathology with normal XR pathology rules. So 4-1 is right here. And we're asking what is the chance for 4-1 to be affected. So we go according to the parents. So they are right here. And what is the chance for the father to be affected? Well, if we go to the XR rule book, okay, maybe I did not write it down, but the father cannot, or a male cannot be, because if we look at the pentagram, male can absolutely not be a carrier and not be affected. If he is a carrier, he has to be affected. He has to be colored in. Why? Because the male carrier type only has one X chromosome. And if that X chromosome is faulty in any way, he will absolutely not have any reserve X chromosomes to rely on, and therefore he will be affected. While the female carrier type has two X chromosomes. So if one is faulty in any way, the second one we can rely on, and therefore we will not be affected. So if we go back, this male right here, is he affected? Is he a carrier or anything? We know for absolute certain that he is not a carrier. There's 0% chance. Why? Because if he was a carrier, because of his carrier type, which is XY, if this was a carrier, he would be affected. He would be colored in. So we know for sure he's not. So we're going according to the mother now instead. So this mother we can't really know anything about. We jump up to this mother we can't really know anything about. But her sisters, so this person and this person, do have affected sons. So therefore we know for absolute certain that these sisters are carriers. Why? Because the fathers are not carriers, and even if they were, they wouldn't have given it to their sons, because the only chromosome that they give to their son is the Y chromosome. So we know for absolute certain that it is the mother. So then we can also assume that this mom right here is also a carrier, as long as we don't include the idea of de novo. But I don't think the colloquium questions will be that difficult, hopefully. So we go to this person right here, and we can go according to the half rule. So it would be half of 100, which would be 1/2, right? However, there is something you need to remember for XR, and that is, if I remember here, if the woman has sons and all of them are healthy, we have to do a Bayesian table for this woman's probability to be a carrier, where the conditional probability, or CP, becomes 1/2 by the power of the amount of healthy sons. So if she has one healthy son, it would be 1/2 by the power of 1, which is equal to 1/2. So we go back, we have to do a Bayesian table. Why? Because this woman right here has not one, but two healthy sons. And therefore, we're casting doubt on the fact that she has this high of a chance of receiving a dominant, or this a pathological X chromosome. So we have carrier, non-carrier here. There we go. All right, so for posterior probability, it's of course what half of what your parents has, which is 1/2. And for non-carrier, it would be 1 minus 1/2, which is equal to 1/2. For joint probability, it's, or sorry, these two are mixed up. There we go, CP and JP there. For conditional probability, like I said, it's 1/2 by the power of amount of healthy sons. Which in our case, and be careful here because you may assume that this is a son immediately because he's in line with other sons, but he is actually not connected to this woman at all. It's only this woman right here. So she has 2 healthy sons, which would be 1/2 by the power of 2, which is equal to 1/4. And right here we have, let's see here, just a second. Right here, of course, for a non-carrier, we always have a conditional probability of 1. Now for joint probability, we just take this times this, which would be 1/8. And for non-carrier, it would be 1/2, but we want the denominators to match. So we write 4 out of 8 here, and we get 1 out of 5. Why? Because we take the numerator up here, and then the denominator for this one would be the numerator here plus the numerator here. So the updated probability would be 1 out of 5. Now we go down to this woman right here. She would of course have half of what her mother has, and half of 1/5 is 1/10. However, if we look at her children, we can see that she has not 1, not 2, but 3 healthy sons. Remember, all of them have to be healthy for this to work. So we do a Bayesian table for her as well. One-tenth. And then here it's 1 minus 1/10, which is equal to 9/10. So 9/10. And then for conditional probability, it's 1/2 by the power of amount of healthy sons, and she has 3 healthy sons, so that would be equal to 1/8. And then for non-carriers, of course, 1. And then here we do joint probability, which is the 2 previous ones multiplied with one another. And then here we can write it as 9/10, but since we want the denominators to match up, we just multiply it by 8 here. That is equal to, there we go. And now for posterior probability, we just take the numerator up here, and then the numerator for the left side plus the numerator for the right side. So 1 plus 72 equals 73. Finally, we know her probability, updated probability, and that is 1 out of 73, so we can take that away. And now, finally, we can do the final calculation for this kid right here, because we know what the mom has, and it's enough to only know the mom's probability of being a carrier for XR pathologies. So we take 1/73 times this child's probability to be affected. And what is that exactly? Well, if we remember, the child's probability to be affected has to rely on the fact that he would only have 1 X2 to rely on. So in this case, it would be this, because this is the female carrier type, and she has this healthy X to rely on, so it doesn't matter if she has this sick one. Instead, we're looking at this right here, and it's just 1 out of 4 in total, right? So we have to write 1 out of 4, and that is equal to a number that I don't have written. So let me just use my calculator. 73 times 4. 1 in 292. There we go. So that's the end of that one. We go next. We have a autosomal recessive pathology with an incidence rate. Okay. So let's first look at this one right here. Incidence rate means that sickness is occurring. Okay, 1 per 8,100 times. And what do we know about AR for population frequency? Let's see here. If question does refer to population frequency, which is does right here, incidence rate is 1 out of 8,100 newborns, then we want to know 2PQ always. The factors are as following. 2PQ equals to heterozygous population frequency with this phenotype. P by the power of 2 equals homozygous healthy population frequency, or this phenotype. Q by the power of 2 is homozygous sick population frequency, which is this phenotype. And then P is just healthy allele frequency, and Q is sick allele frequency. So in reality, we can take these and multiply by one another times 2 to get our heterozygous population frequency. Now, what exactly do we have here? Actually, we have Q by the power of 2. Why? Because if we're dealing with AR, then in order for a child to be sick, they have to have this phenotype. So that's why we're dealing with Q by the power of 2 here. That is equal to 1 in 8,100. Now we can solve for 2PQ by just taking the square root of Q by the power 2. So Q, then that would be the square root of 1 out of 8,100. That is equal to 1 in 90. And now 2PQ, well, let's actually solve for P so that people understand. So P is equal to 1 minus Q. Did I write that down? I did not, so that's unfortunate. But 1 minus Q equals P. P plus Q equals 1, so you can write it down as 1 minus P equals Q as well. It doesn't matter. Let's see here. So P equals to 1 minus Q. We can write it as 1 minus Q, which is this one. 1 out of 90 equals 89 out of 90. And for P, always, we can always round it up to 1. So actually calculating for P isn't that necessary. So now we take 2PQ and we take 2 times P, which is 1. Again, not that necessary to calculate. Times Q, which is 1 out of 90, which is equal to 2 out of 90, or 1 out of 45. So that's our 2PQ, right? And why is it interesting? Well, we want to know for 1 to be affected. And this is his mother, which is from the population. So 2PQ equals 1 in 45. Why don't we do it for all populations and individuals? Because it's not necessary. It's not going to be any great significant out-teller or sign for us to keep going. Instead, we just go according to the direct parent of the child that's from the population. And now we're interested in the father, because again, it's autosomal recessive, and we need both the mother and the father's chance. So the earliest affected would be these two. That would mean that these two are heterozygous. Why? Because they're healthy, so they have to have a dominant allele, and the children are unhealthy, so they must have gotten 1A each from the parents. Now, we can go according to this person, and we can say that this person, since now we don't have anywhere else to go, because we have no way to find out heterozygous probability, we take heterozygous probability of a first degree relative and divide it by 2. So every first degree relative of this person would be 50% of what this person has. And if this person has 100, then this person will be 50, or 1 out of 2. And then this person would be 1 out of 2. Siblings would be 1 out of 2 as well. Also children, but we know that these children are affected, so it's not that important here. Now we do the same for this father and his sons. So half of 1/2 is 1/4. And now we finally have what we need to calculate. So that would be the father's probability times the mother's probability times the probability for this child to be affected. We've done this before. If we look at the Punnett square for autosomal recessive, the chance for a child to be affected, meaning they have both recessive alleles, if both parents are heterozygous, is 1 in 4. So right here, it's 1 in 4. And this is equal to 1 out of 720. Okay, next up is autosomal dominant with a penetrance of 75% chance. What is the chance that 4-2 will be affected? So this person right here. So what do we know about the affected? Well, a lot of people make the mistakes of going from this starting point, but you actually want to start with the nearest affected person. So if this person is affected, what does that mean? Well, let's look at the AD rules. Let's see here. If the parents are healthy and there is an affected child and one of the parents has a history with a dominant allele, that parent is 100% heterozygous. So if we look at this parent, he has a sick child and he has a history of this sick illness, he will be the heterozygous carrier 100% of the time. So this person right here has 2 parents, and one of the parents right here has a earlier history with this heterozygous allele, so he has to be 100% a carrier. Now you may ask, well, in that case, shouldn't we just do 1/2 here? And that is true. A lot of people, though, would also assume that it's just 100% here as well, because look at this line, this means that they are twins. However, remember that in order for them to have the exact same phenotype, not only do they have to be twins, they have to be monozygote twins. So this line is not enough. They have to have like an additional line here, kind of looks like an A, in order for them to have the exact same phenotype. So in this case, we do the half rule out of this. But since it's autosomal dominant, if we're autosomal dominant, every time we are unsure about something, we have to do a Bayesian table for autosomal dominant specifically. So now we're unsure about this person being a carrier. So let's do there we go. So 1/2 there. 1 minus 1/2, which is 1/2. Where did I get the 1/2? Well, that's because it's 50% of that. And then conditional probability is the chance for the person to be healthy and skip the penetrance. So if the penetrance is 75%, the chance to be healthy is 25, or 1 in 4. Excuse me. All right, and then for non-carrier probability, for conditional probability, it's of course 1, because you will always be healthy if you're not carrying a dominant unhealthy allele. And now for joint, it's just that times that, which is 1/8, and then here it's 1/2, which can be converted into 4/8. And then for the final posterior probability, we just take the numerator here, divided by numerator here plus numerator here, which is 5. Okay, Now we know the actual chance for this person to be a carrier. Are we interested in the mother? No, because she's from the population and we only need one of the parents in order for the child to be affected, because it's an autosomal dominant. And remember, what is the chance for a child to be affected in autosomal dominant? If we look at the Punnett square that we drew before, here it is. One of the parents is a carrier, another parent is not. It's 2 out of 4, or 1/2 chance for a child to be receiving the dominant allele. So we take the parent's chance of being a dominant allele carrier, right, times the child's chance to be receiving said dominant allele. But even if the child receives the dominant allele, it doesn't mean that he or she will develop the symptoms, because again, it's a 75% penetrance. So we have to add in the penetrance, and 75% in fractions are 3 out of 4. And this is equal to 3 out of 40. There we go. Let's go to the next one. Early onset autosomal recessive. What is the probability that 3-1 will be affected? 3-1 is this person right here. And then we also know the incidence rate, which means we know the population frequency, which means we would know this person. So 1 out of 6,400, because we get it from here, equals Q by the power of 2. That means that Q is equal to 1 in 80, because you just take the square root of that. P is also always equal to 1, so that means that 2PQ is equal to 180 times 2 times 1, which is equal to 280s, or 140. So we know immediately that this person has a 1 in 40 chance to be heterozygous carrier. Excuse me. Now we want to know this person's chance. So we can see immediately that he has affected siblings, and some of you would assume immediately that we just do 2/3 here, because affected siblings, it means that he has to have 2/3 of a chance to be heterozygous carrier. However, you're forgetting something. And if we look at the rules again, for that 3/4 or 2/3 rule, if parents are healthy and there is an affected sibling, okay, only if parents are healthy, the chance for the sibling to be heterozygous is 2/3. But if we're looking here, one of the parents are actually not healthy. One of the parents has those alleles. And then if we draw up a Punnett square for this case, we know that this person is also a carrier. Why? Because these children must have gotten one from the dad and one from the mom, right? So here we can immediately see that this person does not have 2 out of 3 chances, but we know for sure that he can't be any of these because he is healthy. He has to be one of these. And what are the chances for this person to be heterozygous carrier? That is, of course, 100%. Why? Because he must have gotten at least one of the recessive alleles. And since he's healthy, the other allele would be a dominant one, i.e. heterozygous. Okay. So now we know the fathers, we know the mothers, so we can do a final calculation here. So if the father has 100, the mother has 1 out of 40. What is his chance for the child to be affected? Remember the Punnett square. Right here, it's 1 out of 4 chances for AR. So 1 out of 4, that is equal to 1 in 160. All right, next one. This one is the exact same as question number 2, right here. So if you know this one, you will know this one as well. It's the exact same one, I believe. Yeah. All right, so going next to number 8. Here we have autosomal dominant pathology with penetrance of 40%. We can write it up immediately. 2 out of 5 penetrance. What is the probability that 4-1 will be affected? 4-1 is this person right here. So immediately we look at the parents. We can't really assume anything there. But the closest relative that is affected is that person, right? And then remember, for AD, not AR, you will immediately think that it's 2/3 here, right? Because, one affected child, 2 unaffected parents, it has to be 2 out of thirds. However, that's only for AR, not for AD. Okay? So in this case, we just assume the 1/2 rule. So 1/2 because it's 100% that this person is a carrier here. And now we do the Bayesian table, because if we're unsure, we always do the Bayesian table for autosomal dominant. So carrier, non-carrier. 1/2 here, 1/2 there. Conditional probability is the rest of this amount of people, so it would be 60%, which is equal to 3/5. And then right here, it's just 3/10, I believe. That would be 3 out of 8. Why? Because you take this, put it here, and then for the bottom, you take this plus this. All right, so we got this person's probability. Now we go down to this person, and he would have a 3 out of 16 chance because it's half of his parent. So 3 out of 16, that looks like a 10. And now we do a Bayesian table there too, because again, we are unsure. So 3 out of 16 for the posterior. Conditional joint, not posterior, but prior. And for non-carrier side, you have to take 1 minus the carrier side, so that would be 13 out of 16 here. Conditional probability is the same as before, so 3 out of 5. 1 here. And then the joint would be, the joint is 9 out of 80, I believe. And then right here would be 65 out of 80. And then we take everything together, 9 at the top right here, and then 9 plus 65 at the bottom, which would be 74, which is what we get for this person right here. 9 out of 74. And now we can calculate for this person, because we only need 1 parent's probability to be heterozygous carrier for the autosomal dominant. So we take 9 out of 74 times 1/2, because that's the chance for this child to be receiving a dominant allele, times the penetrance, which is 2 out of 5. That is equal to 9 over 370. There we go. Next up, XR recessive. Remember, with XR, It's not lethal, we're not doing Haldane's law here, but we can immediately assume that if these two kids are affected, this mother is 100% a carrier. Why? Because her husband cannot be giving his sick X to the children, nor is he himself sick. So we know that. Daughter here is 1/2, daughter right here is 1/2, but remember, we do Bayesian table for X-linked recessive if we are unsure about the probability of them being heterozygous carrier, as well as if they have healthy sons. So in this case, both of them have healthy sons. So we assume we go first for this one. That would be 1/2 conditional, non-conditional prior. Sorry, not conditional carrier. Sorry. There we go. Conditional would be 1/2 times amount of healthy sons. She has 2 healthy sons. That would be 1/2 by the power of 2, which is equal to 1/4. Here is 1. Down here is 1/8 because that's this times that. And one here would be 1/2, but we can write it with 2/4 to make the denominators the same. Here we take the numerator up here, divided by the numerator plus the numerator there. So that's 1/5. So it's 1/5 here. Excuse me. Sorry, I think I'm being sick. Anyways, so that's for the mother right here. However, should we calculate for her? And why? First of all, you can assume that it's a healthy son, so we should make a Bayesian table for her. But is it really necessary? Look at who this person has as the parents. Both her as a mother and him as a father, right? So that's the father, that's the mother. However, if the father is unaffected, what is the chance for him to give his son a sick allele? Even if he was affected, what is the chance for him to give his son a sick allele? 0%, because the only allele he will, or the only sex chromosome he will give him is the Y chromosome, which we are not dealing with on an XR recessive pathology. So that's why immediately we know the mom and we times it by the chance for this child to be affected, which we know will be, oh, I did not write it down, but we know it's going to be 1/4. Why? Because for a person to be affected, they have to be a male and they have to be carrying the unhealthy X. They can't be female because females have that healthy X. So it's 1/4. That is equal to 1 in 20. Next up is number 10. And number 10 is the same as this one in terms of pedigree, but it's a little bit different. We're looking at 3/4 instead of 4/3. So we're looking at this person right here. And remember that we did calculate for this mother's chance to be a carrier according to her 2 sons, right? Her 2 sons right here. And now we can do the same for this mother. However, she also has 2 sons. So in that case, and because they have the same prior probability because they're sisters, she will have the same posterior probability as her right here that we calculated here. So she would be 1/5. And now, since we know the father is not affected, just take 1/5 times the chance for this child to be affected, which would be 1/4, and that is equal to 1 out of 20. Same as we did up here. Next up is an AR pathology question. And here we want to know the chance for 5-1 to be affected. So this person right here. So for AR, we know that if people are affected, their parents have to be, when they're not affected, they have to be 100% heterozygous. And that also means that we do the half relative rule. So these people have half a chance, parents, siblings. So she's sibling with him. And the same with her. So that's 1/2 there. And then we do an additional half. So 1/4 here. 1/4 here. I'm sorry, I don't know what's happening. And then we do a 1/8 here. So that's the mother, that's the father. Take the mother's probability times the father's probability times the chance for this child to be affected. And for autosomal recessive, it's always going to be 1 out of 4. So 1 out of 4, which is equal to 128. Okay. Next up. I don't know what's wrong with me today. We have an 80 pathology with 70%. So it's autosomal dominant. We have 70%, so we can immediately write it down. What is the probability that 5-1 will be affected? So this person right here. We already did this when we went through the rules. Now remember how I said that if we have monozygous twins, they have like a little line in between this triangle shape. Looks like an A. And that means that whatever phenotype this person has too, because they're monozygous twins. So if this person has a sick child, what does it mean for this person? Because this person has a previous history with this illness. And remember, any person with a previous history with an illness that is unaffected, that has a child that is affected, means that they are 100% a carrier. So that would be 100% here. And because he has a monozygous brother, it would be 100% here as well. And now we go down one step here. We go according to the half rule, but because we're dealing with autosomal dominant, if we're unsure, we have to write a Bayesian table. So like this, carrier, non-carrier, prior, conditional, joint, posterior, 1/2 here, 1/2 here. And then for the conditional probability, it's whatever is left from this. So it's 1 minus 7 out of 10, which equals to 3 out of 10, because it's the rest of the penetrance population, right? So here it would be 3 out of 10. This would be 1. And then we get to 3 out of 20 for the joint. And then here would be 10 out of 20 if we immediately want to equalize the denominators. Then here would be 3 over 3 plus 10, which is 13. So this person would have a 3 over 13 chance now, not 1/2 anymore. Then we just calculate that. Take the mother's chance to be a carrier times the chance for this child to be receiving a dominant allele from the mother times the chance for this child to be part of the penetrance people because we want to ask for the chance for this child to be affected or to be sick, and only 70% of the people who have this allele are actually sick. And this is equal to 21 over 266. Okay, next up we have this question right here. Autosomal recessive. And here it's really easy to make the mistake. We already have a frequency of heterozygous. And what is the frequency of heterozygous? We'll look back here. You see here, heterozygous population frequency is 2pq. So if the question already gives us the frequency of heterozygous, then we already know our 2pq. That is equal to 1 over 80. Right? Because otherwise, if we did the whole 2pq and q by the power of 2, then this would say the frequency of affected, or the frequency of children affected, or something like that. But in this case, it's heterozygous, and we know that that is 2pq, which means that this is equal to this 2pq. Alright, and which person are we interested in? We're interested in this person, and that is the population person, so she would be 1 over 80 there. Now for this guy right here, we can go according to him down here. And this guy is affected, meaning his parents are 100% carriers, since it's autosomal recessive. Now we go according to the 1/2 rule, so it would be all of the people that are 1 degree relatives with this person would be 1/2. So we can just write 1/2 everywhere. But we are actually interested in this person right here, because we want to know this guy right here, because we need both parents' probability for autosomal recessive, okay? And now we can just take half of him, so it's going to be 1/4. And that is your final calculation. So you take 1/4 times 1 over 80 times the chance for this child to be affected. Because it's autosomal recessive, we're dealing with this Punnett square right here. It's 1 out of 4. So let's go down. That is 1 out of 4, and it will be equal to 1 in 1,280. Alright, next question. Autosomal dominant with a penetrance of 50%. We can write it down immediately. 1 out of 2. What is the chance that 4-1 will be affected? It's this person right here. Now, if we go according to the lineage, we can see right here that this person is affected by the dominant disease. So the chance for these people to be carriers are 1/2. But these people aren't that interesting. Instead, we're more interested in the parents. So if one of the parents are affected, then the children will all have a 1 out of 2 chance to be affected as well. But because we're unsure, because it's autosomal dominant, we have to do a Bayesian table. So carrier, non-carrier, prior, conditional, joint, posterior. That is 1/2 and 1/2. And then the rest of the penetrance, which is 1/2, or 1 minus 1/2, which is 1/2 as well. 1 there, 1/4 there, 2/4 to equal as the nominators. Then it would be 1/3 right here. So 1 out of 3. Okay, sorry if that went too quick, but here I just took this one on the top, and then on the bottom I took this plus this. Okay, and now we can do the mother right here. She would have half of 1/3, which is 1/6, but because we're unsure, we're doing a Bayesian table for her as well. And I will just make this a little bit quicker to try to get an early rest. Oh man. So it would be 1/6 here, and 1 minus 1/6 here is 5 out of 6 here. And then for conditional probability, it's the same as before. It's 1/2, 1 here, 1/12 for joint, and then for joint on non-carrier, it would be 10/12. And then we take the numerator up here, which is 1, divided by 1 plus 10, which is 11. So she would have a 1 out of 11 chance updated. And then this child, for this child to be affected, they need one of the parents' chance to be a carrier times half, which is the chance for this child to be receiving a sick allele from mother, times the penetrance, which in this case is 1/2. And this equals to 1 out of 44. 1 out of 44. Okay, next question. I believe we already did this one, if I'm not mistaken. No, we didn't. Alright, that's good. Let's see here. Early onset AR pathology with an incidence rate of 1 per 8,100. Incidence rate means homogeneous sick, so Q by the power of 2, which is equal to 1 divided by 8,100. So Q would be equal to 1 by 90. And then 2PQ, because P is always equal to 1. That would be 2 times 1 times 1 over 90, which is equal to 2 over 90, or 1 over 45. So now we know the probability for the population mother to be a carrier, and that is 1 over 45. Now let's look at the dad right here. Let's go according to his lineage. Remember, because we're dealing with AR, one sibling is affected, parents are not. Then the subsequent unaffected siblings will be 2 out of 3 chances of being heterozygous. Now we go one step down, which is just 50% of 2/3, which is 1/3 right here. And then finally, if there's a 1 out of 4 chance to be affected by AR, which we know by this table right here. Oh, sorry, right here. So it's 1 out of 4. So meaning that we have right here a 1 out of 4 chance for this child to be affected, times the chance for the mother to be a carrier, times the chance for the father to be a carrier, and this will be equal to 1 over 540. Next up is autosomal dominant pathology with 90% penetrance, so let's write that down. What is the probability that 3-1 is heterozygous? So be very careful when reading the rules or the questions. If they're asking for heterozygous, it's one thing. If they're asking for affected, it's another. So let's look at 3-1 right here. It would be this person right there. So this person, we can go according to their parents right here. We know for sure that this parent would be 100% a carrier because they're affected. So they would give their child half a chance of receiving that dominant allele, but because we are unsure and it's autosomal dominant, we have to write a penance, or not a penance, a Bayesian table. So it's 1/2 there, 1/2 there, and then the rest of the penetrance would be 1 out of 10, because 10%, which is the rest of this. And 1 there, 1 out of 20, and then 10 out of 20 here. And then we just take the numerator, so 1 divided by 1 plus 10, which is 11. So this person has 1 out of 11 chance. Oh, sorry, not that person. This person has 1 out of 11 chance of being a carrier. Then we take half of this person to apply to that person, which is 1 out of 22. But again, we are unsure, and we need to do the Bayesian table right here. And in that case, we're doing something like this, or carrier, non-carrier, posterior, conditional, joint. It's not posterior, prior. I always do that mistake. There you go. Alright. Prior probability is half of what the mother has, and if the mother has 1 out of 11, then the posterior probability will be 1 out of 22. That's just half of 1 out of 11. The non-conditional will be 1 minus 1 out of, 1 in 22, which is 21 in 22. Then we have a conditional probability of 1 in 10, just like before. And then joint probability is 1 over 220. And over here we would be 210 over 220. And then we take the nominators for the top, and then numerators for the top, and the numerators for the bottom. So 1 divided by 1 plus 210, which is equal to 1 divided by 211. That is it for this question right here, because they specifically asked about if this person is heterozygous or not, or the possibility for them to be heterozygous. Next up is an autosomal recessive dominant type. They're asking what is the chance for 5-1 to be affected. So again, we have an affected person here. The sibling has to be 2/3. The parents have to be 100%. Why is the sibling 2/3? That's because we have the rule right here that if the parents are healthy and there is an affected sibling, the chance for the healthy sibling to be heterozygous is 2 out of 3. And now we want to get back to this person, because for autosomal recessive, both parents have to be taken into account during the calculating part in order to determine whether this person has a chance or not of being affected. So half of 100 here is 1 out of 2. And then over here, it would also be half, so it's 1 out of 4 for all the first degree relatives. And then finally, one step below that would be 1 out of 8. So the total amount would be 1 out of 8, which is the father's chance to be affected times the mother's chance to be not affected, to be heterozygous, times 1/4, which is the chance for the child to be affected. So both receiving both sick alleles from the parent. And this would be 1 in 48. Okay, we're almost there. Next up is autosomal dominant with 60% penetrance. That's 2 out of 5. What is the probability that 4-1 will be affected? Right there. So we can go according to this person. It's autosomal dominant. That means that this person has 1/2 chance of being affected. But because we're not 100% sure, we always have to do Bayesian table for autosomal dominant where we're not sure. So 1/2 here, 1/2 here. And then conditional, joint, and posterior. So it would be 2 out of 5. Why 2 out of 5? Sorry, this is 3 out of 5. See, I'm so good at math. 40% would be 2 out of 5, which is the chance for you to be not sick if you're carrying this allele. It would be 1 here, 2 out of 10 here, and then 5 out of 10 there. So that would be 2 out of 7, because you take 2 from this, and then the 7 you get from taking 2 plus 5. So this person has a 2 out of 7 chance of receiving or be inhibiting a dominant allele. Now we can do the calculations for this child because we only need one parent for this. So it'd be 2 out of 7 times 1 out of 2. Why 1/2? Because that's the chance that this person has to receive a dominant allele from their mother. And then times the penetrance, which would be 2 out of 5 in this case. Oh, sorry, 3 out of 5. That's 60%. That is equal to 3 out of 35. Next up is autosomal dominant pathology with the 90% penetrance. What is the probability that 3-3 will be a heterozygous? So 3-3 is right this person. And we know for sure that they have a sibling that is affected. That means that the parent that has a previous history of this illness will be 100% a carrier. Meanwhile, her daughter will only be half. But since we're dealing with autosomal dominant, we have to apply Bayesian table. So here we go, 1/2 here, 1/2 here. Conditional probability is the rest of the penetrance. So if the penetrance is 9 out of 10, this would be 1 out of 10 and 1 out of 20 and 10 out of 20, then 1 out of 11, because the 1 I get here, and then the 11 I get from summating this plus this. So here would be 1 out of 11. That is it for number 19. Now we only have 3 left. Starting from this one, it's AR pathology right here. So with AR pathology, we want to make sure the chance for this person to be affected. So let's look at the nearest affected relative, which is this person right here. And if this person has 2 A's, one of the A's has to be donated. To their child. And since this child is not affected, they also have to have a dominant allele. So it's like this, and that's 100%. And now this person is from the population, and we do have a population frequency here of amount of affected or incidence rate in the population, which is 1. So Q by the power 2 is 1 divided by 1, 2, 9, 6. And only Q would be equal to 1 divided by 36. So use your calculators always, please. And now 2PQ, because Q or P is always equal to 1. This will be equal to 2 times 1 times 1 out of 36, which is equal to, let's see here, 1 out of 18. Yeah. Yes, perfect. So this person has a 1 out of 18 chance of being a heterozygous carrier. Now we take the parents' chance of being carriers times the chance for the child to inherit it or be affected. That is a 1 out of 18 times 1 times 1 out of 4. Why 1 out of 4? Because that is the chance for a child to be affected. Please draw a Punnett square if you're confused. This will be equal to 1 in 72. This one is an exception. And it's, of course, based on Haldane's law. Why? Because if we look at the XR video here, Haldane's law is in case of a lethal pathology and also in case if it only affects one male. And of course, it has to be XR as well. So let's look at here. It's XR. It is lethal. They're telling us that. And it also only affects one male. So in that case, it means that the mother is always 2/3. So the mother of the affected child is 2/3 the chance of being a heterozygous carrier. For the daughter, she would have half of what the mother has. And half of 2/3 is 1/3. Now we can just easily calculate what the unborn child has. We're not interested in the father because the father can only give a Y chromosome to a guy. So he's completely irrelevant in this case. So we just take the mother's chance of being a carrier times the child's chance of being born a male and a carrier, which is 1/4. That is equal to 1/12. Now for the final calculation. We have autosomal recessive. And we're asking what is the chance for one to be affected. For one is right here. And we know that the father is 100% heterozygous or homozygous carrier. The mother we're not sure about. But we can go according to the lineage. So if this guy is 100% a homozygous carrier, pathology carrier, then these people also have to be heterozygous carriers because one comes from the mom, one comes from the dad, and they're both healthy, so they both have to have the dominant allele. And if we remember our AR rule, if parents are healthy and there's an affected sibling, the chance for the healthy sibling to be heterozygous carrier is 2/3. So unhealthy sibling here, healthy parents. So the healthy siblings around are going to be 2/3 chance. Now we just do the 50% rule, which would be 50% of this, and that is 1/3. Now finally we can calculate the chance for this child to be affected. We take the mother's chance times the father's chance, and we know it's 1 because he will 100% give one of the homozygous, the sick alleles. But because the father is a carrier, we should write it up like this. So the mother has a chance of being this. The father is 100% this. So even though you may assume that during autosomal recessive, it's always 1 in 4 chance for the child to be affected, just like this. But that is in case both parents are heterozygous carriers. In our case, right here, the father is homozygous and affected. So it will look like this. And now, the father will 100% of the time give the recessive allele to the child. So it's up to the mother's recessive gene to see if she will actually give the recessive gene to the child or the dominant gene. In this case, for this child to be affected, which means they have to have both recessive genes, that's 2/4 or 1/2. So in our case would be times 1/2. That is equal to 1/6. I hope you guys enjoyed this. This was really quick, just to go through the calculations real quick to make sure that you guys will have it easier with the colloquium. I hope you have a nice day, and we'll see you next time. I'll see you next time.